splicing is such a hands-on activity that you really kind of have to put your hands to it to really understand some of the nuances that are there.
And this is someone speaking who has vast experience as a field technician and fiber splicer, who has worked in R&D and product development, and is currently a product manager at AFL. And today we're going to discuss with them how to really get the perfect splice, because this is what's all about it. You want to have a low loss connection, and the splicing will certainly help with that. So we're going to deep dive into best practices and what to look out for when doing different kind of fiber type cabling splices. So without further ado, I would like to welcome Lucas Mays to the interview. You are listening to Become Fiber Minded, a podcast about fiber optics. Each week we are bringing you insightful conversations with industry experts so you can become fiber minded as well and get the success you deserve. I'm your host Christian Till, and you can follow me on fiberminded.com. Welcome to Become Fiber Minded. Welcome, Lucas, to the Become Fiber Minded podcast. I'm glad you're on.
Thanks for having me. Pleasure to be here. Cool to do this, and hope that this is helpful for a number of folks listening.
My pleasure. From your point of view, Lucas, what kind of splicing tools should technicians start with in order to work in, for example, FTTH?
That's a great question, because I was even going to ask first back, what market segment or what application might you be referring to? So FTTH is a good one, obviously very relevant to just a lot of what's been going on in the recent history that we're all aware of. And just as we're doing, even things like this, it's so crucial to have, good connections, and fiber certainly is a great medium for that. So the core alignment splicer is where I'll start, simply because it's the tried and true technology. It's been around for the longest time, and it's kind of morphed over the years as far as how core alignment is achieved. But more recently, really being the past 20 years or so, you see this little two-dimensional image of, 2D image of fibers coming on screen, and that would be what we call a PAS, or profile alignment system. So a core alignment splicer with a profile alignment system is really just the best security insurance. I like to use the term insurance because everybody understands insurance, right? It's a safety net, it's a backup, it's there in case you need it. And the core alignment does that simply because when you go to put two fibers together, regardless of whether there's dirt or contamination in your V-grooves, whether there's, some sort of poor geometry as far as where the core is relation to the cladding, or even with some of the newer technologies that we've just released, even if you have bad cleave angles, the core alignment splicer allows you to get a good splice with near noise level loss, even amidst these troubles and conditions that can kind of naturally arise when working out in the field in these rough ADTH conditions. So a core alignment splicer is a great starting point. Another one that's a popular option would be an active cladding alignment splicer. And a lot of the reason for maybe choosing that latter option, so it's not going to give you quite the insurance as far as splice loss. Some networks, the way they're designed, they're built to allow for a bit more of a loss penalty towards the premise that you're splicing the fiber to. So then an active clad splicer still gives you a good enough splice for the loss budgets you need to hit. And it's usually a much more portable splicer, so they're going to be more of a handheld or just smaller kind of form factor for those tighter, awkward spaces that you might find yourself in an FTTH environment. And it's another good option. And again, it's also just a bit more budget friendly for some folks out there that, maybe you only do it a few times a year, and you want to have that option in case you need it to accept that work. Nobody likes to turn work down. So, that's a good budget friendly option to have in your back pocket if you want to take on that work as well.
Okay, thank you. And you mentioned now the core alignment and the active alignment strategies. What are the kind of losses one can expect comparing both together?
Yeah, another great question. So we actually have a white paper that really kind of takes a real deep dive into this if you're really interested in really the data behind it even. So we did like a more recently, it's been kind of done over the years, but the past couple of years we did really an experiment where we took fibers of what we would call good geometry where the core is very well centered into the cladding, and then we took some fibers that were poor geometry, where the core is maybe not very well centered in the cladding, and we spliced both with a core alignment machine and with an active cladding machine to understand really what is the difference that a customer should expect. So with a lot of modern quality, I'll call it good fiber, good quality fiber, for a core alignment splicer, a dot oh 01, dot oh 02 is absolutely the kind of expectation and really what you should nominally see out in the field, assuming you're following, of course, all the best practices. And so we're kind of setting those to the side for now. I'm assuming that the technicians are all doing, the right things to give the splicer, of course, what it needs to make a good splice. And so, dot oh 01, dot oh 02, they're certainly very repeatable. The distributions that you'll see in that white paper in particular are very tight to that dot oh 01, dot oh 02 space. And when you get to active cladding alignment with those same good quality fibers, you can certainly still achieve dot oh 01, dot oh 02 splices. But as I mentioned with the insurance earlier, you're just not going to be quite as repeatable at that dot oh 01, dot oh 02. So you'll see even in that data, you see the distribution tails into the higher loss zones. So even though dot oh 01, dot oh 02 is possible, you're going to see some dot oh 04, dot oh 05, even 0.1s from time to time, even with better quality fibers. And again, that's just due to variation, splice to splice, cleave angles, atmospheric conditions, electrode wear. There's a lot of things that go into that. So again, you can get the good splices there, but you'll see some high flyers, let's say. Now with the poorer quality fiber, something that's like an embedded fiber that's been in there for a while, so you're splicing to existing cable. That's why we did this other category of worse geometry fibers to simulate some of these embedded cables that have been out there for a long time. And when you get into that realm, the core alignment really makes a difference, because in that realm you're still going to see your dot oh 02, maybe it creeps up to dot oh 03, let's say, still pretty insignificant, but your cladding alignment splicer then is going to start to see 0.1, 0.15, 0.2 types of splice losses, and that's just because it has no ability to find the core positions with those two fibers and align based on that. And when they're not well centered, all it's doing is aligning the outer edges of the two fibers together. And so who knows where the core is at within those fibers when you're using an active clad splicer. So that's why you're going to start to see the losses really drift up, especially as you're splicing to embedded cables or maybe just a fiber that, a bad lot or something like that got off the line and, has a little bit of a loss penalty.
Perfect. Thank you. Yeah, you mentioned your application note. I'll certainly link this in the show notes, so everyone who's interested to really deep dive into the numbers and the data you have collected over the years is more than welcome to have a look at this. The other follow-up question on this, you mentioned obviously the best practices. Now we bought a splicer, but actually, what are the best practices and how to best use it and to get actually these kind of low losses you described?
So that's very crucial. So the splicer, it's a machine, and all the splicer cares about is the two pieces of glass that it sees, aligning and splicing those. But everything up until that point is completely in your control. And that's why having the best practices is so crucial, because if some of those best practices are not followed leading up to, and so when you go to load in the glass every time, it's a poor quality glass or dirty glass, that's the most common one. The splicer can only do so much, right? So best practices are absolutely key. A few things, just go with the basic prep steps. So we say strip, clean, and cleave. So that's stripping the coating off of the fiber, whether it's your 250 or 900 micron. Strip clean, cleaning it, of course, cleaning the bare glass with your appropriate lint-free wipes and fluid. Not just any off-the-shelf, pharmaceutical fluid. Like, you really do need to use an optical grade fluid. We always tell folks 99% or greater purity, and then there's others, like I said, optical grade fluids that are out there you can acquire, and it's very crucial you use those, because some of those that are a lesser tier as far as purity or are not rated for optical grade cleaning, they're going to leave excess liquid that can be problematic. They're not always going to pull off all of the contamination as cleanly, because we're talking about micron-sized particles here. This isn't like the dust that I see on my desk whenever I wiped it off in a little bit. This is stuff smaller than my hair, and I can't see it with my naked eye. And so that's why it's so crucial to make sure you're cleaning with the right equipment. Yep. And then lastly, cleaving. So same thing with cleaning your fiber. You make sure your cleaver is clean. Make sure the blade is clean. And these are things that man, it's so much stuff to clean, but it's really as simple as just having a kind of a clean procedure. Like For example, a lot of times if I can help it, I try to like wash my hands even before I go to splice. It's like something that I think people don't normally think about, but like your finger oils and debris and things from your hands will just get everywhere, everything you touch, of course. And so you're touching your cleaver, you're putting fiber in, you're sweeping the trash away, whatever you might be doing, you're going to be depositing junk all over your cleaver. And so keeping your cleaver clean so that way whenever it hits that blade and makes that perpendicular end face needed for a good splice, you don't have dust and junk in the way that's hitting the glass at the same time. I want that blade only and those pads that grab the fiber only to be touching, nothing else in between. So anybody listening to this that's been splicing for a while is probably sitting here rolling their eyes because they've heard clean, 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 clean. But man, I'll tell you, even just working with our repair team locally, we have veteran splicers that have been doing this 20 years, 25 years, and they remind us frequently that they've been doing it a long time. But we can look at through a microscope, and we do have to do that a lot of times to see the dirt and debris. We can prove it's there, and we can we clean the thing, give it its good art calibrations, and the splicers then rip it and roar and ready to go back out into the field. But it is such a crucial thing, and it's still the most common problem we see as far as equipment failures or downtimes or issues.
You mentioned the equipment failure and also the cleaning itself. I would think that working cleanly also increases the lifetime of splicing device itself. So also with the cleaving itself, there's a diamond blade inside the cleaver itself. What kind of lifetime values or how many cleaves can I do without really needing to send it out for repair?
Yeah, good question. So, a lot of the depends on the cleaver. They're all going to have different specs and blade lives. We would tell folks that like for our cleavers, a single position, so a single spot on the blade, about 1,250 fibers is roughly the lifetime. But that is kind of really an average or nominal number. We certainly see them go much higher than that, and we see them sometimes a little bit lower than that too. Even if all practices are maintained, it does ebb and flow as you go throughout the blade. And you might ask yourself, well, why? Shouldn't it be a kind of the same number throughout? It's one blade, right? The thing is, this blade. So it is the tip of this blade is sharpened to a 1 micron radius. The blade tip is a 1 micron radius. As a little fun fact. And when you think about 1 micron blade radius, think about the little, think how easy it is to dull your kitchen knife by nicking it, on the cutting board or something like that. That's nowhere even near the level of sharpness that these blades are. So, even dust and debris, whenever it's hitting this hard glass, it's a small piece of glass, don't get me wrong, but it's still a hard piece of glass. And so when you put dirt, debris and stuff in between that, it's just going to increase the likelihood that you might chip even just a little bit of that blade away at certain locations. And so that's where that cleanliness piece, as you kind of alluded to, definitely increases the longevity of your equipment. Another one with the cleaver that people take for granted, I think, is the pads. So if you kind of envision a cleaver in your mind when you lay the fiber down, you have the pad that's like to the left of the blade and to the right of the blade that the fiber lays across before you actually close it and it cleaves. So those pads are usually machined. It's like machined rubber, and not just any type of rubber either. It's a machined specific type of rubber to a very, very flat surface. And if that surface is not flat, as it absolutely can be, if it's bumpy or what have you, even at like a micron level, that'll cause the fiber to kind of be held at different heights from before and after the blade. And even things like that will cause you to have a bad cleave angle. And so when you have dirt and debris resting on your pads, and so you can imagine if I got like a thick layer of debris on my left pad, as soon as I put my fiber down, well, now it's up higher on that one side than it is the other. So now it's going to be at an angle to the blade rather than straight, perpendicular to the blade. And so that's going to cause you cleave error issues. And you might be sitting here going, what the heck? I swear I cleaned my fiber. My fiber's clean. I put it in the splicer. It looks clean. What's wrong with my cleaver? Or what's wrong with this cleaver? And it could just be dirt and debris on your pads. And if you don't keep those clean after pressing and closing, over and over and over again, sometimes you can kind of pit those pads. Like we see a number of cleavers that come into our repair facility, and the pads themselves are actually kind of chipped and dented and little small specks that they're little. Almost think of like a divot in a golf green, kind of spread throughout the pads, and that's just going to cause that uneven surface for the fiber to rest on and give you some cleave issues. So that's just small things that I think are not thought about or maybe just not known. When it comes to why cleanliness is so important with all of your splicing equipment.
Okay, and let's say I have this kind of cleaving problem and my angle is not correctly. Would then the device tell me actually that I need to re-cleave and then redo the cleaving, or what are the measures in place? So me being a new technician.
Yeah, so pretty much all the splicers these days, of course, have some sort of alarm that says, "Hey, this cleave angle is too high." Okay, nominally you're going to see that higher cleave angle and then go, okay, crap, I got to reprep. But I'll go ahead and tell you, I know a lot of people don't always listen to that alarm because maybe they've already reprepped twice and they're just trying to get through the darn job so they can go home, and so they go ahead and splice anyway. Sometimes they get lucky. So I'll tell you right now, sometimes you get lucky and you'll get it to pass through and shoot it with a trace and it's fine, and so you go on about your life and you're just happy that it worked out. Other times it's a new truck roll and you got to go back out there and break it down, break out the closure or the if you what we were talking about FTTH earlier is what we said, your mounted box on the side of the building or whatever, and break it back out and address this splice. I would say two things. One, it's usually always better to listen to the machine. But then secondly, there's some newer splicers out there today that will compensate for the cleave angle. If you have a slightly larger cleave angle and the splicer would tells you, hey, by the way, your cleave angle is a little high. And I'll give you an example, like on our core alignment machine, 3 degrees is the kind of default threshold. Once you get a cleave angle larger than 3 degrees, it's going to say, hey, by the way, you should basically cleave angle too large and suggest you reprep it. But so I'll mention it on here since we're talking about this specific thing. We just launched the 90S Plus, which is our latest core alignment splicer, and it includes a feature called active fusion control, which when it sees that high cleave angle, it then makes changes to the arc, the fusion of melting those two pieces of glass together, and still gives you a good splice loss even if that cleave angle is a little too large. So basically, those guys that had been getting maybe lucky in the past or had truck rolls, now you can basically assume that you're going to get lucky about every time and give you that good loss even when your cleave angle is a little high. Now, granted, we still always tell people, even in light of this new feature, we're going to tell people, hey, it's still best to have good cleave angles if you can help it, so maintaining all the practices we've been talking about. But that alarm's going to be there. And then even unique to our splicing equipment, so if you have too many of those bad cleave angles, so say you load one, it's a high cleave angle, splicer will go ahead and splice it and give you a good loss with that active fusion control. But if you get too many of those in a row, the splicer's still going to say, okay, hey, your blade's probably not good and needs to be rotated. Like maybe you've got a high count on the blade. You're getting to that 1250 or higher, or maybe you damaged the blade on accident and you didn't know it, something like that. And once that happens, it's going to then say, hey, let's go ahead and rotate your blade. And it'll send a signal to your cleaver, and that blade will rotate for you to get you to a new, fresh position and try to get you back to those new, good quality cleave angles. So those are some of the safeguards in the machines these days to help prevent some of those bad splice installations due to poor cleavers or just poor quality fiber prep or what have you. So we try to include some passive benefits to make the process more robust, because we get it. Like, you're just not going to be able to maintain a perfect, flawless process every time, every environment, over thousands of splices. So some of those passive things that just kind of happen as you're splicing to keep you good losses in the midst of whatever environment you're in are, I think, pretty important to enabling the highest level of success for any technician.
Perfect. Thank you. You mentioned that the splicer will automatically adjust the arc. I think this is also true splicing together different fiber types in general. So you have different splicing programs. Is it also adjusting the arc, or how does it work?
Good question. So we have an app note that actually kind of briefly talks about the feature I just mentioned, the active fusion control in relation to cleave angles, because that's kind of the new one, but it does tie in some of those other elements that you just referenced. So this app note talks about how what we call an automatic fiber discrimination function. So what it'll happen is when you have it in that splice mode that does the automatic fiber identifier, you're going to put both fibers in, okay, left and right. You prep them. They're in the splicer. They're going to come into the field of view of the splicer, and yeah, you may not have known exactly what type of fibers they were, and I'm not sure the knowledge level of a lot of our listeners here, but so you have multi-mode and single mode, but even within single mode, it's not all just single mode. There's a lot of different fiber classifications of single mode. You have non-zero dispersion fibers, you have non-zero dispersion shifted fibers, you have low water peak, zero water peak. You have your nominal single mode. You have your bend and sensitive fibers. So and those are all single mode. When you put your fibers in, not all of those splice the same way, and to get you the low reliable loss you need. So when you put those in, the splicer is going to bring those into the field of view, and you'll kind of see the splicer zoom in, zoom out, and it kind of, it's doing this little scan. It's going to kind of look at the brightness lines across that 2D image, that PAS image I mentioned earlier, and from that, it's going to then go, okay, this is bend and sensitive fiber. This is standard single mode fiber, and it'll give you a label on each side for the two fiber types that you're splicing, and then it's going to say, okay, now that I know what these fibers are, here's the best arc parameters nominal for this type of combination. And so it's going to apply those fusion splice parameters to that current splice. And when you go to leg your next fibers, if for some reason, that was your last fiber on that job, and you start the next day at a new job, and you didn't change anything other than now that you have two new fibers in, and now it's single mode and NZ, non-zero dispersion. And it's going to then look at that and go, okay, this is different, obviously, than what you spliced last time. So now we got to apply a different set of parameters, and it'll do that automatically. And then, of course, splice, as you stated. So,
okay. Obviously, as you described, when we splice together the bend and sensitive fiber and also the standard 652 fiber, for example, which is for those who want to really go into this, these kind of fibers have different standards, and they are standardized in the ITUT. And this is usually the terms you're going to hear in the field, which 652A, which is most standard fiber, and the 657 fiber, for example, is as Lucas mentioned, the bend and sensitive fiber. And these are typically also used in FTTH. So for drop cable, what we see is the bend and sensitive fiber being used for the drop cable, and maybe for the horizontal cabling, then the 652 fiber.
Yeah, and I'm glad you say that too, because that's, I think maybe a lot of times people don't even think about like, oh, it's all single mode. They just think single mode. But like, what's important to remember is that that situation you just described is a perfect one of like, here's a real world example that's pretty common, and those are two different fiber types. And so you probably see this more than you even may realize that you it's out there. NZ is another. I mentioned that one already. It's a very peculiar fiber. It's a 655, and that was largely used in big fiber rings, many years ago. So it's not as common, but it's out there, and people splice to it at times, and we'll get those calls sometimes. Like, what the heck is my splicers? What's going on with my splicer? And like a lot of times, if they have it, we'll say, hey, can you send me the trace results? For us to try to figure out what's going on, because the splicer looks like it's behaving. And then you'll see something like that where you see like an excessive loss or an excessive gainer in the OTDR trace in one direction, and they're like, yeah, look at this loss is terrible. And I'm like, hey, well, did you bidirectionally shoot it? If you do that, you'll see it average out differently, because these are two very different fiber types being spliced together, and they're just not going to look the same as a standard SMF to SMF splice.
Yeah, I do get these calls as well.
Actually, you're also familiar with those frequent questions, and yeah.
I mean, it's frustrating for the splicer. I mean, not knowing this, and he resplices 3-4 times, shoots a trace, and then is suddenly doubting his experience and his skill set.
Yeah, that, and then we usually see is it's one of the two. Either it's the OTDR's fault or it's the splicer's fault, and which one's fault it is. I don't know how it gets decided upon. Maybe it's a coin flip at times, but yeah, it's like it ends up one of those. And so, but yeah, to sympathize, I do understand it's obviously a tricky situation and important one to know of. You may not run into it every day, but obviously when you do run into it, it can really increase the time that particular job takes, and you might then start losing money on a particular job because you're having to do so much rework to it, type of thing. So it's like these little nuggets of information are so important to saving you time and energy in the long run.
Yep. The loser gainer Lucas describes is really coming from the mold field diameter differences of the fiber itself. So typically there's a roughly 1 micrometer difference of the mold field diameter. So the mold field diameter is describing the amount of light or the size of light inside the core which is traveling. And since we are using a reflectomy approach with OTDR, depending on the mold field diameter, more or less light is reflected back. And hence we see an attenuation or a gainer, which is like an amplification, which is not possible in a passive system. So that's why if you see huge gainers or huge losers, you need to do bidirectional OTDR testing. You do not see this kind of behavior if you do usual light source power meter loss measurement, because then the mode field diameter has severely a small impact of the overall loss itself.
Yeah, right. And it's just so interesting that, and I think people don't necessarily understand that, why do I see it here on my trace? But yet, yeah, when I do my light source power meter, my olds testing, I don't see that. And it's just, it's like apples to oranges when it comes to testing. They're not the same. And that's, I know a lot of people don't understand that. But yeah, that's why.
Okay. The other topic I had on my list is we see now the emergence from ribbon fiber cables. So previously ribbon fiber cables were most predominantly in data center market, but now we also see the inside moving into the telco market, FTTH as well. So what's the difference splicing ribbon to loose tube, for example?
Yeah, good question. So I'll answer this kind of on two fronts. So to the first one, you talked about some of the applications. So I actually just sat on a webinar even yesterday that talked about fiber and 5G, and it was a Lightwave broadband technology review webinar hosted, and they were even talking about kind of what are the needs, what's the play for fiber and 5G. And one of the things that just stuck out to me as I was listening is some of these guys that are actually the ones installing the fiber talking about how, yeah, I was installing 72 counts, and now I'm installing 144 counts. And even here recently, I've gotten some requests for like some 576, 432. So they see these fiber counts increasing, and they were even talking about how a lot of these folks the reasons they're getting these requests is because some people are like leasing dark fibers, so they want to kind of have some excess fibers for leasing purposes, or others are pulling fiber just for future prep, for future proofing their past, because that they get and they understand that the 5G and other Wi-Fi 6 technologies are increasing those data rate needs and those latency and lowering latency requirements. So you got to have faster latency. And so a lot of this is handled on the active optics side, but a number of it's handled on the passive side too, and it namely leads to just more fiber. So they're wanting to have a few extra fibers, so when they start then getting those upgraded modules for their high data rate needs, they have those fibers already there. Because as I'm sure a lot of the listeners probably know, installing the physical layer of communications is pretty expensive, and you don't want to have to do it twice if you can help it at all. So that's why we see these fibers, ribbon fiber, starting to make its way down closer and closer to premises at times than we have traditionally in the past. And so differences as far as splicing it, it's a totally different splicer. So the loose tube or single fiber splicing, stranded cable, as we hear folks here in the U.S. name it, the core alignment and cladding alignment splicers I referenced, of course, are the prominent splicers. That's what people use. When you get into ribbon, you use something called a mass fusion splicer or a ribbon splicer. It just depends on how you call it for that day. And rather than being a single V groove that moves and aligns these two fibers in some sort of space, you have 12 V grooves left and right. So 24 V grooves, but 12 on the left, 12 on the right. And you lay both of your ribbons on your left side, your right side, and all 12 of those fibers are falling into these 12 V grooves. And the thing is like, I think there's a lot of similarities between the two. I mean, when you think about it, it's fibers coming together. There's an arc between electrodes. It's melting and then fusing the fibers together. However, when it comes to prepping the ribbon versus a single fiber, you definitely have some differences that you have to keep in mind. So for one, the biggest one is like your stripping tool. You're not going to use the little handheld stripper, the little single fiber tool, handheld grip and pull tool. You're going to use something called a thermal stripper, which is actually going to be a flat blade. It's going to first heat the coating of the ribbon, and then that blade is going to help pull it off. So the heating softens the coating, causes it to expand and kind of pull away from the glass, and then that blade digs in and then pulls it away now that it's been kind of loosened off of the glass. And so that's kind of a big difference. And then cleaning is even more painful. We've already been harping on cleaning, and I'm sorry to say, but ribbon splicing, it's even more crucial, because with the core alignment and active clad, the V grooves move. And so if you have some dirt in your V grooves that cause that fiber to kind of kick off an angle or something, well, the splicer will compensate for that by moving those V grooves. The mass fusion or the ribbon splicer can't move those V grooves. They're stationary. So as soon as you have some sort of micron sized piece of junk in those V grooves, that fiber is no longer sitting in that V groove as designed. It's now elevated or kicked off to the left or something to that effect. And so having V groove cleanliness is even more important with ribbon splicing. So you're doing the basic steps of stripping the coating away, cleaning the bare fibers, cleaving the fibers, and then splicing them, of course. But there just are some little kind of nuancy differences that's almost hard to explain just in a conversation like this. You really do have to get your hands and feel it and do it and see it. Splicing is such a hands-on activity that you really kind of have to put your hands to it to really understand some of the nuances that are there. But to put it in a nutshell, that's certainly the key differences. The last thing I'll say too is a lot of people back in 20 years ago, 15 years ago even, mass fusion was also avoided or shied away from because of the loss penalty, the splice loss penalty that you a lot of times see with ribbon splicing. And a lot of that was due to those geometry issues with fiber that I mentioned. So when the core was not very well centered in the cladding, that would cause you misalignment of the two cores. And again, because those V grooves don't move, it's just pushing those fibers together in hopes that they line up. And if the cores are not well centered with one another, you're going to pay a loss penalty. However, glass quality certainly has improved, and we've even got a technical paper that kind of talks about this from 2018 that goes into some studies we did on ribbon fiber splicing and different combinations of dissimilar fibers, same fibers, and just kind of looking at what are the losses that are typical. And we actually even saw in some modern fibers average losses of .03 for a ribbon splice. So it's like if I can get away with a .03 splice loss on a ribbon fiber, like, I mean, hey, I'm going to do that all day long because I can splice 12 in one go as opposed to a single in one go.
Awesome. And what is your recommendation if Klarna had the crazy idea to splice together a loose tube to a ribbon fiber?
Awesome question, actually. So a lot of folks, of course, single fiber splicing, core alignment's been the bread and butter for so long. And ribbons fibers were, yes, data center or maybe like high central office back-end service provider applications. And sometimes when they would take those fiber rings and start to get closer to the different branches in those large fiber count rings, service providers would run into that same thing where they then are now dealing with a loose tube to a ribbon. So in that instance, there's this kind of tried and true method called what we call a ribbonizing tool or a fiber arrangement tool, where you stack all of your individual fibers just side by side in this little bitty slot that it's like just tall enough to fit a single fiber in. And so you can kind of imagine it just makes this little horizontal stack of your 12 fibers, and then you apply some little glue or paste and slide that across the fibers that are sticking out of that tool and make your little temporary ribbon. And then people could, once you have this little temporary joined 12 fibers, you now have a quote unquote ribbon. And so you then mass fusion splice those. Today, we actually really have seen recently a pretty darn cool evolution in that particular application where rather than using the glue and the paste to make a temporary ribbon, there's some tools now on the market where you can arrange those 12 fibers. It brings them all, stacks them together for you, and no glue is required because it goes straight into the fiber holder. And so your fiber holder is what's holding those 12 fibers now in line with one another for stripping, cleaning, and cleaving and splicing, as opposed to having to have some glue that does that for you. And so you get rid of A, the cure time for the glue, B, you don't have to deal with shipping a hazardous material. If it's in your bag, a lot of times it's not a big deal, but for people on the back end, procuring this material, since the glue is considered hazardous by logistics standards, it's sometimes you have to pay a little bit more for the shipping or have certain codes in place to be able to transport it properly. And then you also get away with just the mess. I mean, granted, if you do the process correctly, you're doing a pretty good job of not getting too messy, but we've seen plenty of mass fusion splicers that the V grooves are littered with that temporary glue. It kind of flakes off, or too much was used, or it was on somebody's fingers and they touched their V grooves, things like that. So getting rid of that glue, I think, is a huge plus. One of the common questions I've gotten whenever we show this tool or these glueless tools, they go, what if I have to reburn? Because they're not all 12 held together. I got to open my fiber holder, right? And so now they're not held together anymore. I'm actually probably here soon going to be putting together a video that shows exactly this process. But if you're basically just careful and that you put your thumb on the ribbon in the holder right behind that clamp. So basically instead of the clamp holding the ribbon in place, you're just doing so with your thumb. You just open the clamp at that point, kind of just slightly pull on the nose, because you only got to pull it like a few 20 millimeters or so to get you enough length then again to be able to strip clean and cleave. Kind of just hold it with your thumb, grab the little bit of fiber sticking out the nose after the clamp's open, pull it forward, close the clamp again, and resplice. So it's a little bit of finesse, don't get me wrong, but I think it's pretty manageable. And again, you still get rid of the glue, and I just hate that stuff personally.
So in your experience, what kind of loss can I get if I use the non-glue way?
So the non-glue and the glue way are going to give you really the same losses. I think the non-glue way just does free you of more room for operator error. We talked about the glue can be managed. However, as we've seen in our repair facilities, it's not always. So more opportunity for debris and contaminants to get into your V-grooves or your cleaver is, of course, just more room for higher splice losses. So getting rid of that glue kind of takes out at least one of those contamination factors out of the equation that we don't have to worry about now. So from that standpoint, I would probably say that the glueless is going to be better loss results. Not necessarily in like a 1-to-1 splice comparison, but like your yield, call it your repeatability, your yield over like 20 splices, 30 splices or more. You're probably going to get better results just because that glue's not there to be a possible contamination factor.
Cool. So now we talked about the splicing technology in general. We talked about the mass fusion and ribbon splicing. And as you mentioned, it has obviously come a very long way since inception. So where do you see it to go from here? I mean, the next 2-5 years, will it be robots doing the splicing for us, or?
It's funny you bring up the robots. Of some of the guys I work with, we've kind of teased about that. Even what's it going to look like, and we almost envision this like it's going to go. I mean, gosh, you see robotics in a lot of things these days, and so almost there's the splicer is going to sprout arms, and it's going to pick up the ribbons, and it's going to strip clean cleave it and put them in there, and you kind of just watch the thing go. That would certainly be nice. Well, depends on whose framework you're looking at. I guess if it's the technician that wants to keep his job, he doesn't want that to happen. But from the people buying the equipment, they might like that. So, all kidding aside, realistically speaking, yeah. So we've seen splicing evolve pretty rapidly. I mean, you figure splicing is really fusion splicing of fibers is about a 40-year-old technology as far as when it was first created or invented, and in its rawest form to where it is now. And so given that, we've seen a ton of advancements from its first inception, it was a very manual process. I mean, you were putting these fibers in, and like everything was manual. Bringing the fibers in together was like manual turn dials that you use to move these little stages forward. Even getting the like back and forth alignment once you brought them in close enough together was manual. And you're doing this all by looking through, an eye microscope. It's kind of like looking at a petri dish, like in grade school. It's kind of like what you were doing with these fibers to get these to align together, and then crossing your fingers and hoping that you actually did it right. Because there wasn't like a loss estimation at that time either to let you know whether or not it actually spliced well. It was just kind of a lot of touch and feel, and you kind of knew the machine, and you looked at it and you get, that's not a good splice. And so, it was very, and then now you just wasted 5 minutes because that's how long it took for a single fiber at best. So we've gone from that to where now, dadgummit, you just, like we talked about, you strip clean cleave with some tools real quick and throw it in, and then like with our splicer, even like you don't have to touch anything else. I mean, as soon as you set the fibers in the machine, it closes the lid, it looks at them and analyzes, tells you the fiber type, tells you the cleave angles, adjusts your splice if needed for the cleave angles, the fiber type, splices, opens, you slide your sleeve in and throw that in, and it automatically closes and heats. And so all that's done fairly hands off from what it used to be. So moving in the future, we have some interesting technologies that like I kind of keep my eye on that are developing, and we kind of wonder if they'll take off and if people will start to adopt things like multi-core fiber. I don't know if you've heard or much of that, but today we have fibers that have a single core, of course, inside the 125 micron cladding, but we're talking about fibers that might have not just one but 4 cores in a single 125 cladding, or maybe not even 4, maybe 7 or 8, or it's some crazy numbers have been thrown out, like even like 32 cores in a single fiber. And so, which is insane to think about actually, but from like a data center especially application, you can see the benefits there. You're running thousands and thousands and thousands of fibers into a single building at times, and think about the physical aspects to this, how much weight you have in cable trays overhead, how much time it takes to splice that many fibers. and then all the individual items that's connected to, and what they of course have to pay for heating and cooling. And airflow is a huge thing in data center environments. And so if you have bigger cables and bulk cables and stuff, that's technically blocking airflow and things like that. That's they've monitored to like a crazy high level of accuracy to understand the efficiencies of cooling and stuff in their data centers. So they're looking for anything they can do to reduce size, weight, time. Time is such a big one. And so when you think about packing 32 lines of communication into that one fiber, you can see why that's attractive to them. So there's things like that. If we can overcome some of the challenges, especially on the active optics sides of things, the actual transmitters and receivers, it's outside of my realm of things, but those challenges can kind of be overcome. It's a very attractive option. Honestly, there's some technology things that have to come up to speed with that, but it certainly makes sense on paper. Another one that's recently we've seen is like hollow core fiber. So that one's really interesting. So fiber that doesn't have glass in the middle of it, it's literally air where the light travels, and then depending on the design of the fiber, sometimes even throughout the cladding, they have air pockets dispersed. That's a totally different side of splicing. And when it comes to splicing those two fibers together, as we've actually done a little bit of testing of that ourselves, it can be done actually even with some of the splicers today. However, it does take a very different set of arc parameters and stuff, so that's something to keep in mind. So new recipes would have to be developed and things like that. But anywho, so those are some of the things we see in the next, call it 5 years or so, where splicing might go that we'll have to make changes to and adapt to if those technologies continue to gain popularity.
I actually believe that the multi-core would be sooner than 5 years. So we already see the multi-core deployment inside submarine cables. So the recent Google cables are all multi-core. Yeah. And absolutely, the hollow core you brought up, I think, is going to be a tremendous change. Transmitting at light speed, all the high-frequency traders will love it. Getting this extra microseconds, less delay.
That's right. Yeah, there's one in use for that specific purpose, so it's starting to get tested a little bit. So, and yeah, on the multi-core fiber side of things, I'd forgotten about that one, but you're right. The submarine cables, the space division multiplexing is kind of one of the big words, the terms that they're buzzing on right now, because as you can imagine, with a submarine cable, you don't want to add more fibers, because as soon as that fiber gets bigger, or as soon as that cable gets bigger, they have to go through a whole new round of standards and part number developments and testing, and that's just so much headache and time and weight and things that they don't want to have to deal with, expense. So multi-core fiber, yeah, definitely attractive for them. And we actually have a splicer that can do multi-core fiber splicing. We've got a white paper on it. We actually recently released a new alignment technology that kind of handles multi-core fiber better, just to try to give some people something to play with for as that application develops. It's not like a traditionally field portable splicer. It's one of our more benchtop style of splicers, because you got to actually be able to physically rotate the fibers to be able to align, the right course to one another. So, we have that capability and are kind of working with it. Yeah, it'll be interesting to see how quickly it takes off.
All right. Thank you for your time. Absolutely appreciate it. I love the discussion. Thank you for your insight.
Yeah, thank you, Christian. And if it comes up and you want to do something else, a slightly different topic or whatever in the future, I'll be happy to come on again.
Wow, what a value bomb from Lucas Mays. Good thing that the robot takeover for splicing machines will not happen in the foreseeable future. We also learned today that for a perfect splice, you need to have the right equipment, and also that cleanliness is a key factor to get the 0 dB splice. Thanks for listening to this episode of Become Fiber-Minded. If you enjoyed the episode, I would appreciate it if you could do me a quick favor and rate and review the podcast. This shows the platform that I'm doing something right and that people like the content. If you learn something new, tell a friend or a colleague about the podcast so I can help more people. Be sure to go to fibermind.com/episode 3 to see the show notes with the links mentioned in this episode. If you have any follow-up questions, you can drop me an email at ask@fibermind.com, and I will collect the questions to do an FAQ episode in the following weeks. Until next time, keep connecting the world with fiber.